And what my colleagues at the Rutherford Appleton lab in Oxfordshire have done is to build an exact replica of a genuine alpha particle scattering experiment, such as Rutherford himself might have done, or at least his assistant Geiger might have done. Geiger, the same Geiger, is in the Geiger counter, by the way. This is the first time on television that a real thing like this has been in operation. Let me just show you what's inside it. It's evacuated, so this outer thing here is just to protect me if the thing explodes while I'm talking to you, and you, of course, as well. Now, at the front, we've got the alpha particle gun. And it shoots the alpha particles at this target. It's a wafer-thin target of gold, the very same stuff that Rutherford's team used themselves all those years ago. Now, most of the alpha particles we expect will pass straight through, so we've got a detector out here that will pick them up. But some of them, if the positive charge is indeed concentrated in the centre of the atom, could be detected by a thing out here at a much larger angle. What we can do is vary the position of this one and see what happens as we do so. Now, most of the alpha particles go shooting straight through, and on the dials at the bottom here, we're keeping count. The bottom dial shows you how many alpha particles are being detected out at the front, the ones that just pass straight through without anything happening. And already, nearly 400,000 have been detected in the forward direction, just shooting through. The bell that you hear ringing is each time something is detected by this fellow at the side. It's such a rare event, we've got the bell there to let you know. Now, the point of this is that if the atom had just been a diffuse ball of charge everywhere, nothing would ever bounce back. The fact that any bounce back at all is the key. That was the genius that Rutherford had to realize it was the once in a blue moon that the bell rang that was showing that the positive charge is concentrated in the middle, and occasionally, when by chance the alpha makes the direct hit, when the red ping pong ball hits the football head on, and it bounces back and be detected in this backward direction. Now, we'll leave this thing running. At the moment, the score is 4 in the backward and 536,000 in the forward. But it's the 4 in the backward that are the crucial ones. And occasionally the bell will ring, and when it does, you will know that here in the theatre, an alpha particle has been scattered by the nucleus in the centre of an atom. You are seeing it proved, or hearing it proved, right here and now. Great. Told you is, but how small is that charge in the middle? And that is where Rutherford's real genius came into play. By the rarity of the ice cream bell going off compared to the frequency of the thing shooting straight through, you may already have had a feeling that the positive charge can't be very big. But Rutherford, by a very simple calculation, showed how small it really is. What we've got here from the Cambridge University Library are the 2 crucial pages from Rutherford's notebooks where he first realized how small the nucleus in his atom really is. His writing isn't the neatest thing in the world, but we forgive him a few things. In here is the one time in the whole of this story I'm going to show you an equation. Another alpha particle strikes just on cue. What he was interested in here were the rare occasions when the alpha particles bounced right back. They came shooting in and were turned around in their tracks. Why do they stop and get turned around? They come shooting in, they're being repelled, sent back where they came from, and for a moment they come to a halt. Because at that moment, the speed, the energy they started with has been exactly balanced by the force pushing them away. And this is what his equation says. On the right-hand side is the amount of force pushing them away. On the left-hand side is the energy his bullet started with, the half mv squared. And he's going to weigh those two against each other at the moment they come to a stop. And so he takes this up this side, and that up that side, and that down there. The higher mathematics is all done. He knows everything on the right-hand side, and he's going to put the numbers in and work out what this distance is. How close in does that little alpha particle get before it's turned around? Because that's going to be a measure of how big that nucleus actually is. So you turn the pages of the book. On the next page, you see this is genuine when he makes mistakes and crosses them out. Not like you or me who erase it and try to get our alpha plus for neat and tidy work. Down here, you see something which the younger members of the audience might not recognize. This is long division. And he makes another mistake, but that's not the important thing. Here is the crucial thing. That distance, the measure of the size of the positive charge that we now call the nucleus, is a millionth of a centimetre. Now, at that moment, Rutherford realises that he's onto something. And his excitement, you can almost see it, because his writing becomes almost totally illegible. In fact, it's only recently I've found out what the second word here is. Let's see if you can read it before I can. Since something, radius of atom is of the order of 100 millionths of a centimetre, to be compared with the millionth of a centimetre. It is seen that the distance of approach of the charge centre is very small compared with the radius of the atom. That is the point. Rutherford has discovered that the relative size of his positive charge is minute compared to the size of the atom. Now, this is really amazing for several reasons, one of which is that at that time, at the beginning of the century, when Rutherford is doing this experiment, or at least Geiger and Mars and his assistants are doing it, but Rutherford, being the clever guy, got the credit, this works marvellously, just what I needed. What he has done is shown, first of all, that even that atoms exist. That second word is probably. Since probably the radius of the atom is. He was even aware they didn't understand everything, and the uncertainty was there. He has shown that atoms really exist, and also that the positive charge is trapped in that little bit in the middle. And that's why he got so excited. And it's from that we now have our picture of the atom, which has survived to the present day. We're a bit short of supporters, but we can bring the atom here to the theatre. Let's suppose that the atom were as big as the theatre. I've brought you a measure of the nucleus in here as well. Can somebody with good eyesight come and help me find this? Nobody with good eyesight. Have you got eyesight? Great. Hello, what's your name?
Alex.
Right, Alex. Now, hanging from the ceiling here, somewhere in the theatre, we've got the atomic nucleus. For those people at the back who can't see it, can you find it?
Yes, just there.
The ball bearing here. Right. Can everybody see the ball bearing? Does everybody agree that that's the atomic nucleus? No. The ball bearing actually is just holding this wire in place. The nucleus is that little knot in the wire that we have added. Thanks very much. Now you really know how small it is.